All right. I know this was your last example. I don't want to spend too much time talking about it, but I do want you to email or present something on the Google Stream to indicate any questions. But notice that there is no overlap between these two things at all. And so that's why you could calculate it a separate way down here. Besides adding up just the 15 that weren't in it, you could take the ones that were in it away from 1. All right, moving on to the next topic, and that is the addition law of probability. And there's a whole bunch of stuff over here. And I'm going to kind of use these little A's and B's to help explain this, what's going on. This D is not in the set. So B is the part that's included in both. So the probability of A happening would be if A and B together were happening. So, and I'm not going to worry about putting it over top of the entire sample space, but that's what it would be. The probability of B happening would be, again, these two occurrences, because they're both included in B. And so the union of A and B, if I just look up here to the union of A and B from last video, it would be these three items are the ones that are in A or B or in both. So the union of A and B would be A plus B plus C. And so notice that if I were to add A plus B to B plus C, the problem is this B would get counted twice. And that happens to be the intersection here. So really the probability of A plus B minus this intersection gives me this union piece, because down here it would be A plus B plus B plus C minus B. And you'll notice what happens if I do that is this minus B and one of these B's cancel, and I actually have A, B, and C, which happens to be the union. So going ahead, the addition law for probability goes with the union. So this is OR, and OR means I add. Kind of said that before, that's the rule. OR means add. But if there is some kind of intersection, if I don't take that intersection away, then that B got double counted. So that's why this minus the intersection is happening. And this is kind of the picture. Union A and B is all that. There's A, there's B, and I got to take away this. Basically, I'm taking away this guy because he's counted here and he's counted here. So he's counted twice, so I need to take one of them away. Now, if you have mutually exclusive events, guess what? Their intersection is 0. It's the empty set, so I don't need to write minus 0 because there is nothing in common. So if your events, if you know they're mutually exclusive or disjoint, then this union, this OR, A or B happening, is just you add up A and B, and you don't have to worry about an overlap because there is none. For example, if I were looking at the set of aces and the kings in a deck of cards, there are no aces that are kings, so if I wanted the probability of drawing an ace or a king, which would be the same as having that little union symbol in there, it would be 4 out of 52 plus 4 out of 52 because there is no overlap. All right, so conditional probability. This is something that definitely shows up on the IB exam. If you have two events, A and B, the conditional probability of A given B, and this is a big deal right here because this is, oops, Mark, I guess I'm trying to draw a heart or something. I don't know. This is your condition. It means that B is your condition. And it means that the probability that A happens given that B has already occurred. So this guy has already happened, and it may have changed the likelihood of A happening. So this little vertical segment literally means, excuse me, A given B. So if you see this notation, it is talking about conditional probability. And there are some of formulas in your formula packet for this. So this is the probability of A given B, and that is equal to the probability of the intersection of A and B divided by B. So what that means is, here's B, it's all of this, right? So this formula means I would take this entire set of values, and the top of it is just the intersection. So that's just this part right here. So the numerator would be the blue part, whatever is in here, and the denominator would be everything that's red, would be the whole red circle. So it's a good way to think about conditional probability in a Venn diagram sense is you're going to take the intersection and you're going to put it over top of one of the circles if you're doing it with a Venn diagram. We can also do this with the tree diagram because this guy right here is going to be one of the branches and the second branch that follows it, and you would be multiplying those because and means multiply. And then probability of B would be everything that happened to be occurring here. So you're going to do one branch is going to go on the top, and this is going to be the combination of a couple branches that you will have had to add together. All right, so there's just the picture of the bottom, and there is the picture of the top. That's the only place where A occurs in B is that shaded region. So if I were to do a little algebra, again, if I were to multiply both sides of this equation by probability of B, that would cancel. And if I came over here and multiplied that by probability of B, notice that that equals the intersection. So the intersection of these two events is a probability of A given that B times the probability of B. And if I just switch the condition, it switches the value of A. So notice that this thing that comes second, the condition, is in your denominator. So this is always in the denominator. And the combination of them, the and of them, is in the top. So now I can play some games. If probability of A is 0.6, the union is 0.7, and the intersection is 0.3, find the probability of B. So there is one formula that combines all of these equations, and that is the formula for the union. So probability of A given B is, oh sorry, this is not a given. A or B is the probability of A plus probability of B minus the intersection. Remember that business? This is horrible handwriting. I don't know what's going on today. So now I can fill this in. I already know this is 0.7. Probability of A is 0.6. Plus, I have no idea what this is. That's what I'm asking for. So I'm just going to leave that as a big B just to save myself some writing. But I also know the intersection is 0.3, so I have one missing value. I just zippity-doo-dah things around. Personally, I would probably combine these two because that would equal 0.3. And then if I subtract 0.3, I get my answer. And the probability of B would be 0.4. Oops, there you go, 0.4. All right. So you're going to try this, and again, this thing you can't see over here, apparently, because my video's in front of it, is probability of B. So give it a go. Pause and on pause. Let's see what you got. Hopefully you did something similar, and you ended up with 0.6. Again, questions, send them to me so I can answer them. All right, I'm going to do apparently A and B1, and you're going to do 2, 3, and 4. So I now have a chocolate. I'm randomly selecting from a box which contains 6 chocolates with hard centers, and this is the word and behind here, 12 chocolates with soft centers. So these are like those boxes of chocolate you get that you bite into and you're like, ooh, I don't like that one, and you throw it away and you try another one. So 6 have hard and 12 have soft centers. H is the event that a randomly selected chocolate from the box has hard center, so that makes sense because that H, and that must mean S is for probability of soft. So first question, are H and S mutually exclusive? So the question is, can you have a chocolate that has a hard center and a soft center at the same time? And the answer to that is you cannot, which means that they are mutually exclusive. So in my Venn diagram, I would have 2 circles that are not overlapped because I have 6 in here and 12 in here. And apparently that means I have no chocolates that weren't one of those 2. So are they mutually exclusive? Absolutely. Find the probability that my candy is a hard center. Well, that's 6. So this answer is 6. And there are a total of 18. So 6 out of 18 or 1 out of 3 chance. Remember, there's no other candies in that box, so I don't have to worry about any other ones. So now you're going to try 2, 3, and 4. Pause it. Watch your notations here and go. All right, video on paused, and we'll finish this. Notice that the probability of soft is your 12 out of 18 reduced There is no intersection, so that probability right there, this is hard and soft. We said no intersection, so that's 0. And the union is one or the other, and that means all of them. So there's a 100% chance that your candy has a hard center or a soft center. All right, moving on. Here we go. Class of 25 students, 14 like pizza, 16 like iced coffee. One student likes neither. So one kid doesn't like either of those things. So they're going to be outside of the circles. And 6 students like both. So again, this is my key right here when I start this. And I'm going to make a diagram. And apparently I've got some kids that like pizza. And I have some kids that like iced coffee. And there is an overlap, because 6 of those kids live in the middle. And so that has to be your first number. Okay, what happened to my marker? I've lost control. There we go. Oh boy. All right, so things are rapidly getting out of control. I'm losing all of my, I don't know what this is. That's just extraneous and gone. All right, see if I can do this again. 6 kids in the middle. These are gone. I have one student that doesn't like either, so that one kid I can put out here. They're gone. Now I'm going to deal with these, and this is going to be my check at the end. So 14 like pizza, so I have to come over here. The whole blue circle has to add up to 14. I can't put 14 here, or I would be telling somebody that there are 20 kids that like pizza. So this has to be 8, because together that has to make 14. And I have, that's gone, 16 that like iced coffee. So again, this whole red circle has to add up to 16, so that has to be 10. So that is the trick with the drawing the diagrams from this situation. You start in the middle, and it helps you build your circles, because these are the people who like pizza but do not like iced coffee. It's different than these kids right here. So all of these numbers should add up to 25. That's 14, 24, 25. They do, so I have correctly filled in my chart. So this helps you figure out if you've got everything in the right place. Otherwise, you'd have more kids than I told you would have. So now, again, I'm asking a probability. I'm not asking how many there are. I'm asking a probability. If I randomly select a student from this group, again, that random is pretty important. We talked about that already, that they like pizza. So this, I know there's 25 kids, and the number that like pizza are right here. All of those like pizza, so that would be include both of them. So that would be 14 out of 25. All right, now how about kids that like pizza, given that he or she likes iced coffee? So this is now basically I'm saying probability that you like pizza given that you like iced coffee. So I'm just going to change this so you see the notation. So iced coffee is my denominator. So that would be the entire red circle. So iced coffee goes in the bottom. Iced coffee is a total of 16 people. The top of this, so again, that would be iced coffee down here. And the top is going to be pizza and iced coffee, remember from our formula. And the top then is just interested in both items, so that is this guy right here. So of the iced coffee drinkers, how many of them, or what portion of the iced coffee drinkers like pizza? Well, it's just this 6 out of all the iced coffee, 16. So this restricts your denominator, it changes it. It's not out of 25 kids anymore. It's only out of iced coffee drinkers. And out of the iced coffee drinkers, what's the probability one of them likes pizza? Well, that has to be one of these 6. So it'd be 6 out of 16, or 3/8 if I reduce correctly. All right, you're going to try one similar. There are no important words over here. This says are majoring in sciences. This is the word and, so I guess that is kind of an important word. This word is an and here. And this is just are. So pause this thing and give this thing a try. You might want to draw a Venn diagram first to get it to go. And pause. All right, let's take a look. There's my Venn diagram. Notice I start in the middle. 15% had both of these, humanities and science. A total of 30 were in humanities, so those add up to 30, 50 there. And again, these weren't given as counts. These were already given as probabilities. So I can just use those values in terms of answering my question. So not majoring in humanities nor science, that's this group right here. Probability of students majoring in humanities given they're a science major, so I'm only interested in my science majors. That's why that's on the bottom, and of that group, that's on the top, and there you go. All right, it looks like I'm going to have to do a third video. I'm so sorry. I can't believe these are taking so long. I shouldn't talk as much. We'll do independence next.